Hello everyone, it's Kodak from 19. Today is day 16 in my challenge day, and today I'm going to do listen the last section in this course, last section in this week of the neural network course. Okay, let's start.
When training a neural network, one of the techniques that will speed up your training is if you normalize your inputs. Let's see what that means. Let's see if a training set with two input features. So the input features X are two-dimensional, and here's a scatter plot of your training set. Normalizing your inputs corresponds to two steps. The first is to subtract out or to zero out the mean. So you set mu equals 1 over m sum over I of xi. So this is a vector, and then x gets set as x minus mu for every training example. So this means you just move the training set until it has zero mean. And then the second step is to normalize the variances. So notice here that the feature x1 has a much larger variance than the feature x2 here. So what we do is set sigma equals 1 over m sum of xi star star 2. I guess this is element-wise squaring. And so now sigma squared is a vector with the variances of each of the features. And notice we've already subtracted out the mean. So xi squared, element y squared is just the variances. And you take each example. And divide it by this vector sigma. And so in pictures, you end up with this.
Sorry, there was an issue on camera, so I just set up again.
This, where now the variance of x1 and x2 are um, both equal to 1. Oh, and one tip, if you use this to scale your training data, then use the same mu and sigma to normalize your test set, right? In particular, you don't want to normalize the training set and the test set differently. Whatever this value is and whatever this value is, use them in, these two formulas so that you scale your test set in exactly the same way rather than estimating mu and sigma squared separately on your training set and test set. Because you want your data, both training and test examples, to go through the same transformation defined by the same mu and sigma squared calculated on your training data. So why do we do this? Why do we want to normalize the input features? Recall that the cost function is defined as written on the top right. It turns out that if you use unnormalized input features, it's more likely that your cost function will look like this, like a very squished out bow, a very elongated cost function, where the minimum you're trying to find is maybe over there. But if your features are on very different scales, say the feature x1 ranges from 1 to 1000 and the feature x2 ranges from 0 to 1, then it turns out that the ratio or the range of values for the parameters W1 and W2 will end up taking on very different values. And so maybe these axes should be W1 and W2, but in intuition, I'll plot W and B, but your cost function can be a very elongated bow like that. So if you plot the contours of this function, you can have a very elongated function like that. Whereas if you normalize the features, then your cost function will on average look more symmetric. And if you're running gradient descent on the cost function like the one one on the left, then you might have to use a very small learning rate, because if you're here, then gradient descent might need a lot of steps to oscillate back and forth, right, before it finally finds its way to the minimum. Whereas if you have a more spherical contours, then wherever you start, gradient descent can pretty much go straight to the minimum. You can take much larger steps. With gradient descent, rather than needing to oscillate around like the picture on the left. Of course, in practice, W is a high dimensional vector, and so trying to plot this in 2D doesn't convey all the intuitions correctly. But the rough intuition that your cost function will be more round and easier to optimize when your features are all on similar scales, not from 1 to 1000, 0 to 1, but mostly from -1 to 1, or with about similar variance as each other. That just makes your cost function j easier and faster to optimize. In practice, if one feature, say x1, ranges from 0 to 1, and x2 ranges from -1 to 1, and x3 ranges from 1 to 2, these are fairly similar ranges, so this will work just fine, is when they're on dramatically different ranges, like one's from 1 to 1000 and another from 0 to 1, that really hurts your optimization algorithm. But by just setting all of them to 0 mean and say variance 1, like we did on the last slide, that just guarantees that all your features are on a similar scale and will usually help your learning algorithm run faster. So if your input features came from very different scales, maybe some features are from 0 to 1, some from 1 to 1000, then it's important to normalize your features. If your features came in on similar scales, then this step is less important, although performing this type of normalization pretty much never does any harm, so I'll often do it anyway if I'm not sure whether or not it'll help with speeding up training for your algorithm. So that's it for normalizing your input features. Next, let's keep talking about ways to speed up the training of your neural network. One of the problems with training neural networks, especially very deep neural networks, is that of vanishing and exploding gradients. What that means is that when you're training a very deep network, your derivatives or your slopes can sometimes get either very, very big or very, very small, maybe even exponentially small, and this makes training difficult. In this video, you see what this problem of exploding and vanishing gradients really means, as well as how you can use careful choices of the random weight initialization to significantly reduce this problem. Let's say you're training a very deep neural network like this. To save space on this slide, I've drawn it as if you have only 2 hidden units per layer, but it could be more as well. But this neural network will have parameters W1, W2, W3, and so on up to WL. For the sake of simplicity, let's say we're using an activation function g of z equals z, so a linear activation function, and let's ignore b. Let's set b of l equals 0. So in that case, you can show that the output y will be wl times wl minus 1 times wl minus 2 dot 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 down to w3, w2, w1 times x. But if you want to just check my math, w1 times x is going to be z1, right? Because b is equal to 0, so z1 is equal to, I guess, w1 times x, and then plus b, which is 0. But then a1 is equal to g of z1, but because we use a linear activation function, this is just equal to z1. So this first term, w1x, is equal to a1. And then by similar reasoning, you can figure out that w2 times w1 times x is equal to a2, because that's going to be g of z2 is going to be g of w2 times a1, right? Which you plug that in here. So this thing is going to be equal to a2, and then this thing is going to be a3, and so on until the product of all of these matrices gives you y hat, not y. Now, let's say that each of your weight matrices, WL, is equal to, let's say it's just a little bit larger than 1 times the identity. So it's 1.5, 1.5, 0, 0, right? Technically, the last one has different dimensions, so maybe this is just the rest of these weight matrices. Then y hat will be, ignoring this last one, which is different dimension, will be this 1.5, 0, 0, 1.5 matrix to the power of L minus 1 times x, because if we assume that each one of these matrices, is equal to this thing, it's really 1.5 times the identity matrix, then you end up with this calculation. And so y hat will be essentially 1.5 to the power of L, to the power of L minus 1 times x. And if L is large for a very deep neural network, y hat will be very large. In fact, this grows exponentially. It grows like 1.5 to the number of layers. And so if you have a very deep neural network, the value of y will explode. Now, conversely, if we replace this with 0.5, so something less than 1, then this becomes 0.5 to the power of L, right? This matrix becomes 0.5 to the L minus 1 times x, again, ignoring WL. But so if each of your matrices are less than 1, then if, let's say x1, x2 were 1, 1, then the activations will be 1 half, 1 half, 1 fourth, 1 fourth, 1/8, 1/8, and so on until this becomes 1 over 2 to the L. So the activation values will decrease exponentially as a function of the depth, as a function of the number of layers L of the network. So that if you have a very deep network, the activations end up decreasing exponentially. So the intuition I hope you can take away from this is that if the weights, W, if they're all, just a little bit bigger than 1, or just a little bit bigger than the identity matrix, then with a very deep network, the activations can explode. And if W is, just a little bit less identity, right? So if this was maybe is 0.9, 0.9, right? Then if a very deep network, the activations will decrease exponentially. And even though I went through this argument in terms of activations increasing or decreasing exponentially as a function of L, a similar argument can be used to show that the derivatives or the gradients you compute with gradient descent will also increase exponentially or decrease exponentially as a function of the number of layers. With some of the modern neural networks, you actually have L equals 150. Microsoft recently got great results of, I think, 152 layer neural network. But with such a deep neural networks, if your activations, your gradients increase or decrease exponentially as a function of L, then these values could get really big or really small. And this makes training difficult, especially if your gradients are exponentially small in L, then, gradient descent will take tiny little steps and it'll take a long time for gradient descent to learn anything. To summarize, you've seen how deep networks suffer from the problems of vanishing or exploding gradients. In fact, for a long time, Microsoft recently got great results of, I think, 152 layer neural network. But with such a deep neural networks, if your activations, your gradients increase or decrease exponentially as a function of L, then these values could get really big or really small. And this makes training difficult, especially if your gradients are exponentially small in L, then, gradient descent will take tiny little steps and it'll take a long time. For gradient descent to learn anything. To summarize, you've seen how deep networks suffer from the problems of vanishing or exploding gradients. In fact, for a long time, this problem was a huge barrier to training deep neural networks. It turns out there's a partial solution that doesn't completely solve this problem, but that helps a lot, which is careful choice of how you initialize the weights. To see that, let's go on to the next video. In the last video, you saw how very deep neural networks can have the problems of vanishing and exploding gradients. It turns out that a partial solution to this doesn't solve it entirely, but helps a lot, is better or more careful choice of the random initialization for your neural network. To understand this, let's start with the example of initializing the weights for a single neuron, and then we'll go on to generalize this to a deep network. Let's go through this with an example with just a single neuron, and then we'll talk about a deep net later. So with a single neuron, you might input 4 features, x1 through x4, and then you have some a equals g of z, and then it outputs some y. And later on for a deeper net, these inputs will be, right, some layer a of L. But for now, let's just call this x for now. So z is going to be equal to w1 x1 plus w2 x2 plus dot 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 plus, I guess, wn xn. And let's set b equals 0. So, let's just ignore b for now. So in order to make z not blow up and not become too small, you notice that the larger n is, the smaller you want wi to be, right? Because z is a sum of wi xi. And so if you're adding up a lot of these terms, you want each of these terms to be smaller. One reasonable thing to do would be to set the variance of w to be equal to 1 over n, where n is the number of input features that's going into a neuron. So in practice, what you can do is set the weight matrix W for a certain layer to be np dot random dot rand n, and then whatever the shape of the matrix is, you fill this out here. And then times square root of 1 over the number of features that are fed into each neuron in layer L. So it's going to be n of L minus 1, because that's the number of units that are feeding in to each of the units in layer L. It turns out that if you're using a ReLU activation function, then rather than 1 over n, it turns out that setting the variance to 2 over n works a little bit better. So you often see that in initialization. Especially if you're using a ReLU activation function. So if GL of Z is ReLU of Z. Oh, and depending on how familiar you are with random variables, it turns out that sampling a Gaussian random variable and then multiplying it by square root of this, that sets the variance to be equal to this thing, to be 2 over n. Okay, and the reason I went from n to this n superscript L minus 1 was in this example, with logistic regression, which is that n input features, but in the more general case, layer L would have n L minus 1 inputs to each of the units in that layer. So if the input features or input activations are roughly mean 0 and standard variance and variance 1, then this will cause Z to also take on a similar scale. And this doesn't solve, but it definitely helps reduce the vanishing and exploding gradients problem, because this trying to set each of the weight matrices W, vanishing and exploding gradients problem, because it's trying to set each of the weight matrices W, so that it's not too much bigger than 1 and not too much less than 1, so it doesn't explode or vanish too quickly. I'll just mention some other variants. The version we just described is assuming a ReLU activation function and is by a paper by He et al. A few other variants, if you are using a tanh activation function, then there's a paper that shows that instead of using the constant 2, it's better to use the constant 1. And so 1 over this instead of 2. And so you multiply by the square root of this. So this square root term would replace this term. And you use this if you're using a tanh activation function. This is called Xavier initialization. And another version worked out by Yoshi Benjo and his colleagues, you might see in some papers, but is to use this formula, which has some other theoretical justification. But I would say if you're using a ReLU activation function, which is really the most common activation function, I would use this formula. If you're using tanh you could try this version instead, and some authors will also use this. But in practice, I think all of these formulas just give you a starting point. It gives you a default value to use for the variance of the initialization of your weight matrices. If you wish, the variance here, this variance parameter, could be another thing that you could tune with your hyperparameters. So you could have another parameter that multiplies into this formula and tune that multiplier as part of your hyperparameter search. Sometimes the tuning that hyperparameter has a modest size effect. It's not one of the first hyperparameters I would usually try to tune, but I've also seen some problems where tuning this helps a reasonable amount. But this is usually lower down for me in terms of how important it is relative to the other hyperparameters you could tune. So I hope that gives you some intuition about the problem of vanishing or exploding gradients, as well as how choosing a reasonable scaling for how you initialize the weights. Hopefully that makes your weights not explode too quickly and not decay to 0 too quickly, so you can train a reasonably deep network without the weights or the gradients exploding or vanishing too much. When you train deep networks, this is another trick that will help you make your neural networks train much more quickly. When you implement backpropagation, you find that there's a test called gradient checking that can really help you make sure that your implementation of backprop is correct. Because sometimes you write all these equations and you're just not 100% sure if you got all the details right in implementing backpropagation. So in order to build up to gradient checking, let's first talk about how to numerically approximate computations of gradients. And in the next video, we'll talk about how you can implement gradient checking to make sure that your implementation of backprop is correct. So let's take the function f and replot it here. And remember, this is f of theta equals theta cubed. And let's again start off with some value of theta. Let's say theta equals 1. Now, instead of just nudging theta to the right to get theta plus epsilon, we're going to nudge it to the right and nudge it to the left to get theta minus epsilon, as well as theta plus epsilon. So this is 1, this is 1.01, this is 0.99, where again epsilon is same as before, is 0.01. It turns out that rather than taking this little triangle and computing the height over the width, you can get a much better estimate of the gradient if you take this point, f at theta minus epsilon, and this point, and you instead compute the height over width of this bigger triangle. So for technical reasons, which I won't go into, the height over width of this bigger green triangle gives you a much better approximation to the derivative at theta. And you want, sort of instead of taking just this little triangle on the upper right, is as if you have two triangles, right? This one on the upper right and this one on the lower left, and you're kind of taking both of them into account by using this bigger green triangle. So rather than a one-sided difference, you're taking a two-sided difference. So let's work on the math. This point here is f of theta plus epsilon. This point here is f of theta minus epsilon. So the height of this big green triangle is f of theta plus epsilon minus f of theta minus epsilon. And then the width, this is 1 epsilon, this is 2 epsilon, so the width of this green triangle is 2 epsilon. So the height over width is going to be first the height, so that's f of theta plus epsilon minus f of theta minus epsilon, divided by the width, so that was 2 epsilon, which we worked out down here. And this should hopefully be close to g of theta. So plugging in the values, remember f of theta is theta cubed, so this is theta plus epsilon is 1.01. So take the cube of that minus, now 0.99, take the cube of that divided by 2 times 0.01. Feel free to pause the video and plug this in the calculator. You should get that this is 3.0001. Whereas from the previous slide, we saw that g of theta, this was 3 theta squared, so when theta equals 1, this is... So these two values are actually very close to each other. The approximation error is now 0.0001. Whereas On the previous slide, with taking the one-sided difference, just theta and theta plus epsilon, we had gotten 3.0301, and so the approximation error was 0.03, right, rather than 0.0001. But so with this two-sided difference way of approximating the derivative, you find that this is extremely close to 3, and so this gives you, much greater confidence that g of theta is probably a correct implementation of the derivative of f. When you use this method for gradient checking and backpropagation, this turns out to run twice as slow as you were to use a one-sided difference. It turns out that in practice, I think it's worth it to use this other method because it's just much more accurate. Little bit of optional theory for those of you that are a little bit more familiar with calculus. It turns out that, and it's okay if you don't get what I'm about to say here, but it turns out that the formal definition of a derivative is, for very small values of epsilon, is f of theta plus epsilon minus f of theta minus epsilon over 2 epsilon. And the formal definition of a derivative is in the limit of exactly that formula on the right as epsilon goes to 0. And the definition of a limit is something that you learn if you take a calculus class, but I won't go into that here. And it turns out that for a non-zero value of epsilon, you could show that the error of this approximation is on the order of epsilon squared. And remember, epsilon is a very small number. So if epsilon is 0.01, which it is here, then epsilon squared is 0.0001. The big O notation means the error is actually some constant times this, but this is actually exactly our approximation error. So the big O constant happened to be 1. Whereas in contrast, if we were to use this formula, the other one, then the error is on the order of epsilon. And again, when epsilon is a number less than 1, then epsilon is actually much bigger than epsilon squared, which is why this formula here is actually a much less accurate approximation than this formula on the left, which is why when doing gradient checking, we rather use this two-sided difference where you compute f of theta plus epsilon minus f of theta minus epsilon, and then divide by 2 epsilon, rather than this one-sided difference, which is less accurate. If you didn't understand my last few comments, all of these things down here, don't worry about it. That's really more for those of you that are a bit more familiar with calculus and with numerical approximations. But the takeaway is that this two-sided difference formula is much more accurate, and so that's what we're going to use when we do gradient checking in the next video. So you've seen how by taking a two-sided difference, you can numerically verify whether or not a function g of theta that someone else gives you is a correct implementation of the derivative of a function f. Let's now see how we can use this to verify whether or not your backpropagation implementation is correct, or if there might be a bug in there that you need to go in and tease out. Gradient checking is a technique that's helped me save tons of time and helped me find bugs in my implementations of backpropagation many times. Let's see how you could use it too to debug or to verify that your implementation of backprop is correct. So your neural network will have some set of parameters, W1, B1, and so on up to WL, BL. So to implement gradient checking, the first thing you should do is take all your parameters and reshape them into a giant
I think now I stopped to recording. Always before I stop, let's recap first. So the first thing that I learned today is how we can normalize our inputs in the neural network. So for example, we have two input features like plotted in this graph, and it depending on the input feature x1 and x2, and we can get an expected value of these samples following this equation. It's so trivial that is familiar to someone who already know the probability theory. And we can just plot the deviation by subtracting, which subtract uh, the mean value from the each of the samples value, and we can plot the deviation here following this axis. And so you can see the variance of x1 is larger than x2 feature, so we can compute the variance of it following this equation, which is mm, in definition, the variance is the average of the sum of a square of deviations. So a lot of, and then after we update the x by dividing the with the standard deviation, which is the square root of variance, we can get a normalized inputs here. So why do we need to do? Because it improves that we can improve our learning algorithm to run faster. For example, if we have an unnormalized input here for the parameter W and B, we may get this bar formed, which is elongated form following the axis. But if we do a normalization on the inputs, we can get this kind of bar form, which is kind of symmetric. But we can be certain, although we can be certain that it always formed as a circle, but actually we can expect this kind of good variance in the inputs. And if we take gradient descent in backpropagation, based on the starting point, if we select a point in this at this point, it may learn faster. Yes, like it can reach the global minimum faster. But if we take this point, it may take longer than this point. So it can be different. It can has a different learning algorithm performance depending on the points it starts. But with the normalization, we got a good variance on the input in features so that we can expect good performance in the learning process without depending on the point it starts like this. It doesn't matter. The next thing that I learned is vanishing and exploding problems in gradient descent. So with the intuition, if all the matrices are bigger, has a larger component value than identity matrix, or if the matrices, weight matrices has a larger value of components than identity matrix, it can be vanished or it can be exploded. Because we have a big, in general, we have a big deep neural network which has number of layers is corresponding to 150 or more than. And if all the matrix weight matrices is larger than identity matrix, by following the multiplication property of matrix, we will get cumulative matrices value, and it is cumulative in the exponential way. So it can be so huge in numerical mathematically. So to avoid this vanishing and exploding problem, we can take care of the initialization on weight matrix. And it turns out that theoretically, if we if we multiply a specific variance to random weights by depending on the activation function we use, we can reduce this problem. Yes, we can reduce these vanishing or exploding gradient descent problems. So in the case of we use ReLU activation function, it'd be better to use 12n as a var. And if we multiply all the components with this square root of this variance, we can expect that we're gonna reduce these problems. For just reference, if we use a tonnage function for activation, we can use the Zapier initialization in this case. And the final things that I learned is a numerical approximation of gradient descent. And as we already learned, we use a gradient descent in the backpropagation. Uh, and to check the whether our implementation is correct or not about the against the derivative part, we can get we can calculate the actual equations on ourselves, but sometimes it may be so difficult to get to derive all the derivatives in the equations process. But however, instead of that, we can take an approach, numeric approximation. So in this case, we can use a two-sided difference by following this formula, and if we comparing it with the true tangent of the on this zeta, it turns out that the approximation error follows the O n square is always smaller than the one side difference. So we got a better way to check and a simpler way to check our implementation of derivatives. So that's all for today's recording, and thanks for your watching.